Welcome to our third session of our six-part solid wood bioheat webinar series. My name is Karen Jackson. I am with the Ontario Ministry of Natural Resources and Forestry, and I will be your host for today's session, which is bioheat combustion systems. Last week, we learned about the types of solid woody biofuels and the importance of their quality from Sebna Madrali with Natural Resources Canada and Vince Rutter with Biothermic. Today, we will focus on technical aspects of the systems that use these solid woody biofuels. Before we move on, I'd like to mention that this session is being broadcast live. In the event of technical difficulties, please have patience as we will be working promptly to sort out any issues. If you happen to miss part of today's session or want to share it with a friend, we'll be providing a copy of the session recording for review online at a later date. I am happy to share that this webinar series is the result of a partnership between the Centre for Research and Innovation in the Bioeconomy, also known as CRIBE, FP Innovations, Natural Resources Canada, and the Government of Ontario's Ministry of Natural Resources and Forestry. On behalf of the organizing team, I'd like to thank you for your interest and for joining us today. Today, our guest speaker is Terence Souvet, an engineer with the Ontario Ministry of Agriculture, Food and Rural Affairs. He is extremely knowledgeable, passionate, and experienced with bioheat combustion systems, and we are grateful to have him here to share his knowledge. At the end of Terence's presentation, we will be holding a question and answer period. To facilitate this session, we will be using Slido as our platform. If you've never used Slido before, that's okay. The system is easy to use and can be accessed from your internet browser. To access Slido, please type the website address displayed here on the screen into your browser, www.sli.do, or you can access directly from an email that was sent to you earlier today from Jonathan Hallis. Once you're on the Slido website, you will see a box to enter a participant code. For today's session, we're going to use the code #BioheatF18, F18 being today's date. If you have questions you would like to ask Terence, please send them over Slido. Other participants will be able to see your questions and can upvote questions by selecting the thumbs up icon to advance questions to the top of the list. In the event we don't get through all of your questions today, we will be posting responses on CRIBE's website. And please feel free to submit your questions throughout the presentation. You don't have to wait until the end. I will give everyone some time to connect to the Slido right now. Okay, now that everyone has had somewhat of a chance to connect to Slido, we're going to send out a poll to make sure everyone has a handle on how it works. We know that there are people joining us from right across Ontario and Canada today, so we're asking, where are you joining us from today? I'll give everyone a moment to submit their responses. Okay, now that we've covered how our question and answer period is going to work, I'd like to welcome Terence. Terence, please feel free to share your screen and video now and begin your presentation.
Okay. Control L, there we go. Thanks, Karen, for the introduction. So session number 3, we're going to try to tackle the topic of combustion and the various options that you can get on the different appliances. Okay. We're going to go over essentially the most what people would remember or recall from looking at emissions for the wood heating appliances. So we're going to talk mainly about particulate matter and how to control combustion. So we're going to talk about the Magic 7. And after that, we're going to talk about the various manually and automatically fed appliances that are available on the market, where we're not going to go into specialty areas or the cook stove or any of the smaller appliances that generate electricity, but they're out there. And then we're going to talk about more of the technology options that are there to control emissions. and secondary emission control. And if we have enough time left, because I'm really looking forward for the questions using Slido, we're going to tackle some things that are different in North America, in Europe, that North America is just starting to take a tackle, and mention the air approvals that you'd require concerning combustion. Since combustion is quite a huge topic to cover, I've used this presentation and webinar from the International Energy Agency. It's with Task 32. So Thomas's presentation is really looking at about 20 years, the past 20 years of research in terms of looking at like toxicity levels of particulate matter, how to minimize them, what could be done. It's been doing a lot of the research regarding that topic. And I'm using a couple of his slides and the way that he's presenting it to us. Mainly what he said is that the modern automatic combustion devices that are tested and operated as per the manual, and also using the standardized biofuels like the wood pellets or standardized wood chips, have a very low environmental impact. And that typically the air quality issues that we see, it's because of the products of incomplete combustion. So the way we measure them is with particulate matter. So there's like PM 10 micrometers and PM 2.5. And also the studies have shown that it's really the products of incomplete combustion in the particulate matter that can cause disease. So there's two types. So the ones that we just mentioned, like soot, tar, polyaromatic hydrocarbons, volatile organic carbon. These are the ones that's going to cause major issues in the body. And then you have the products of complete combustion. These are the ash that's in the wood or the biofuel that you're burning. So it could be potassium, calcium, other salts, and their toxicity level is a lot lower. And they're also quite easy to remove, as we'll see later. So the way that we try to tackle that is you first have to try to control the combustion as best as we can. So the way I come up with this is there are 7 factors. I call them the magic 7 and the triple T's and the lambda. So you do have to try to get the turbulence, the temperature, and the residence time in a sweet spot. And also the next thing you have to look is you have to make sure that you always have the proper air to fuel ratio so that you have complete combustion. So the value we have, we try to promote in the literature and through the test, or the manufacturers are trying to always achieve a lambda of about 1.3, which is about 30% excess air, is also the other term that you'll see or you'll hear. And it's very key that you don't try to choke the combustion or try to put too much air so that it gets too hot, or reduce the combustion air too much, because then you'll have the products of incomplete combustion. There's also the considerations for startup. So for stoves, an example is, as they've demonstrated, that if you start your stove from the top instead of trying to light the fire underneath, you do have a huge impact on the startup emissions. The other one also to consider is the moisture of the biofuel you're using. So, for cordwood, firewood, that's the obvious thing to consider. But also if you have something dry, like if you try to burn, 2x4s or, reclaim lumber in a stove, well, you have too much surface area and your fire is just gonna go like way out of hand. So then you're not gonna be able to achieve complete combustion. So like we said, if you have too much air and the fire is too warm, you'll just essentially be creating a lot of soot, so that you'll have that black particle in there. But if you choke the fire, you'll create a very cold environment, and you'll be creating creosote and all the other ones that are there. And typically, really takeaway here is that some appliances, like we'll see, they're fully automated, there's sensor up the wazoo, and they do a perfect job. And then the other ones that are mostly manual, and you sort of set and walk away, and don't have any sort of feedback for the operator or a controller. They're a lot worse to control all that. So the first way is to reduce particulate matter is that the first measure is to control the magic 7. And after that, you would apply secondary measures. So either there could be catalytic converters that could remove some of the products of incomplete combustion, like the volatile organic carbons. Then the second thing you can remove through the inorganic ash is, well, you can burn like wood pellets that have a very low ash content, and typically that's what people usually try to use, because it does have less operational issues to maintain and operate the wood pellet stove or the furnace or the boiler. But some of the appliances don't have a multi-cyclone or an electrostatic precipitator or bag houses to remove those. So that's why it's key to have lower ash content in these fuels for these smaller appliances. So we've talked about the lambda, or the air to fuel ratio. So a value of 1 is typical for gasoline cars. So you have 1 unit of air with 1 unit of fuel, and you have almost the proper stoichiometric ratio to have complete combustion. In wood, we try to have it around 1.3 up to 1.5, so that you have enough oxygen left to make sure that as the gases continue in the combustion chamber, there's enough oxygen to have complete combustion. So in the A, where you have a very high air excess air ratio, or a lambda value, you'll be creating creosote. I've seen on the diagram. For B, that's that sweet spot we just mentioned. That's where you have the inorganic salts. And for C, that's why you're missing oxygen. So you have a very rich mixture, and it usually happens at elevated temperatures when the fire is just too warm and going out of control. Then you'll generate a lot of this soot, so that particulate that you can remove out of the filter. I would say one thing that is different from wood is that if you try to compare with any of the fossil fuels like natural gas or gasoline, it's heterogeneous, meaning that wood is actually the carbon in wood is composed of 2 different types of carbon. So you'll have about 3/4 that's going to be volatilized, and that's what creates the smoke. And then the other third is the charcoal that's left. So you can see at all the way down at the bottom, number 4, that's all the volatile has been gone, the water has been evaporated, and just left with charcoal. So it's key here for any of the systems that are burning in a batch, that you try to monitor where you are in this step, because as a fire burn, things change all the time, and the air to fuel ratio is just going to be out of whack, and you're not going to be able to maintain proper combustion. And that's what we just is the thing that's hard for people to understand, is that the wood itself doesn't burn. It's the smoke that's contained in the wood that does. And at the end, you're left with the charcoal, and charcoal is actually quite tricky to maintain the magic 7, because most of the time it's really tough to have an elevated temperature. So if you want to do burn coal, it's quite complicated in the devices that are designed to just burn the volatile fraction of the wood. Typically, you probably have too much air and the temperature is too low, and then you get all those 7 factors out of whack. Now we're going to look into the manually fed modern wood heating appliances, and like to point out that even the burn barrels got their act together. So this is a welded barrel. It's used for developing countries. So for people that want to know more about the cook stoves and the stoves for developing countries, there's a list server that monitors really all the efforts and the stuff that the World Bank organization is trying to tackle to reduce smoke emissions in developing countries. So this unit does it's a top lit updraft, and you can that's combustion technology in a burn barrel. So if these guys can do it, we can for sure do it in modern appliances. So we're going to look at the stoves, fireplace inserts, and forced air furnaces, and the boilers. Now we have a list of all the Magic 7 for the stove, fireplace inserts, and forced air furnaces. Typically, the modern units would have that updraft secondary combustion air. So either sometimes it's like just pipes with little holes, and you'll see that flame coming back out. They do help for the turbulence. The temperature is typically low, so that's a design concept. So we're going to touch just a little bit later with the burn rate. It's typically for stoves, fireplace inserts, and forced air furnaces. People would reload, let the temperature go up, and then walk away. So you want to stretch the heat output, and that just design or the request from the customers that just puts an issue in terms of the temperature, because at a certain point the appliance may not be able to control a proper temperature inside the combustion chamber, and that is because of the air throttling issues. So the uncertified stoves were really bad, because people would just close the keys so that it would stretch all overnight. And essentially what happened is you'd have a lot, you wouldn't have a lot of heat coming out, but you'd be smoking, essentially losing a large fraction of the volatiles from the wood. And people wouldn't realize that, because then you would go in the morning, open the stove, and you still see the big piece of wood or half of it gone, and you'll just be left with the charcoal. And then you'd be thinking that, oh, I've burned all that wood a night, but you didn't realize that a lot of the energy from the wood has just gone up in smoke. The furnaces are a lot better at that. They use a thermostatic air damper that does try to control the temperature as the thermostat is calling for heat. In terms of residence time, the furnace and the catalytic stoves have a sort of a larger surface area, so the time that the gases spend in the appliance is a lot longer, and you'll typically see that because um, the stack temperature is a little bit lower than typically a stove that has a similar design aspects. Like I said, for the startup, a lot of people don't do a top lit startup in stoves and furnaces. Now we go into the biofuel issues for cordwood. I could probably spend a whole 45 minute just discussing about that. But typically the way that the appliances are tested, it's with very standardized pieces because it's in a lab scenario, and they're using kiln dried pieces of wood or cordwood, and they're maintaining it in a uniform environment so that they would have a uniform moisture content to do the tests, so that you would be able to replicate the test. But essentially, that's not the wood that we're using. So this is a discrepancy between, designing an appliance to, pass a test with a specific type of wood, but on the other hand, the operator or the suppliers, don't do the same thing. So that's why it's key. We say, burn only dry wood, and don't burn green firewood. Don't try to mix it. Some dry firewood with green firewood, it really doesn't work. In terms of the burn rate, like I just said, the design appliance, it's just it's an issue for all cardwood appliances, is that people want to stretch that heat output, and typically people don't want a large, fast fire. They want it to last all night, and because of that, it would generate a lot of soot. So one of the newer appliances that is in the market do have a better way to control the air to fuel ratio and the temperature. So it does have sensors in the stack to control the air. It's available on the market right now, but it's a little bit more expensive. I think people still don't see the value or the cost benefit here. But for stoves, I think it's really the way forward, and we're probably going to see the same control devices for fireplace inserts, and it may also come for forced air furnaces. So if you do want to know more information, please contact Stove Builder International. They're out of Quebec, near Quebec City. And if you can also go on the Alliance for Green Heat website, and you'd be able to have more information about their wood stove design challenge. So now looking at the outdoor cordwood boilers. So the legacy units had issues for turbulence. There weren't any secondary combustion air. Some that came on the market around mid 2005, 2010 would have either updraft gasification that they call, but it's again pyrolysis that's happening in the firebox, not gasification. So it's really two-stage combustion that they try to do that to reduce the issues with smoke. But the other thing that happened is, again, it's cordwood, so people are putting more wood than they need because they want to stretch that heat output. There's also the bad habit of being afraid that your outdoor wood boiler would freeze. So you again put more wood than necessary. And then you would have a lot of these on-off cycles that are typically seen during the day. So maybe you wake up in the morning, you'd go and reload the outdoor wood boiler so that when you come back from work at night, you'd still have some wood left, and the house would be warm, and you'd have hot water to wash your hand and for cooking and that kind of stuff. So but the issue here is that if it was a bit warmer during the day, essentially the outdoor wood boiler would just try to maintain the temperature through the aquastat, and it would just do an on-off cycle all day long. And you'd be losing a lot of that volatile fraction of the cordwood that you just put in there. For startup, again, that's because of that. I say it's sort of a complicated relationship status here, because some people do put just the amount of wood that they need, and that's typically what they have to do. But then there's some operators that sort of don't get the hang of it and just put a lot more wood than is necessary. And like I just mentioned for the stove, you'd open the boiler when you come back to reload, and it's like, oh, I still have all the wood in there. Like you just see the fixed carbon, but you've lost all the volatile fraction. Another issue with the biofuel is that there's still people out there that just put firewood that hasn't been split. So in the middle, it's still very green, and that would still cause a lot of issues in terms of the Magic 7. And there are modern models right now for outdoor cordwood boilers that are that have passed the emission test. They still have reliability issues because they're non-pressurized. So like the modern units that are coming from Europe, they're typically pressurized and they last longer. But again, the issue is how does the unit are tested in the lab translate into the field? So, in the lab, you don't measure just jacket heat losses, although they say they insulate it anybody that has a hot tub and is paying for electric bill, you know what I'm talking about. But essentially, even if they do now have downdraft two-stage combustion technology for the outdoor cordwood boilers, they typically don't have an air-to-fuel sensor to really try to match some of the key parameters that you have to maintain. So that's yet to be seen. That's a typical example of how they work and how they're set up and hooked up to the house. Now for the European style units, they're typically indoor and they're a lot smaller, so they wouldn't have like a 200 or 300 or 400 gallon water jacket around the firebox to capture that extra heat as they cycle on or off. But they'll have what's called a buffer tank, so they'll essentially be a tank that is separate from the unit. The way that they're set up is that when you put wood in them, it would just run at 100% output and essentially dump all that heat in the buffer tank. So really the unit is very easy to set up and to fine tune. And since it doesn't go into that on-off cycle, you wouldn't have that energy that is being lost throughout the day. And other aspect also that we really don't have time to cover, but essentially when you store all that heat in the buffer tank, you can, on a warm day, only do one fire. You don't need to constantly put wood to make sure that that you're when you're coming back from work or when you wake up in the morning that everything is cold and that you don't have any heat going to the house because you have that buffer tank that is warm and is supplying heat for your house. Also, a startup is a lot more simpler because they come equipped with flue gas sensor, and there's also sometimes an option on the exhaust blower. So the unit recognize that you're trying to start up a fire, so it does try to go a lot quicker and up to temperature. And the other thing here to consider is that if you try to put green firewood or improperly seasoned firewood, it may happen that actually the unit won't start properly or that you won't be able to actually run the unit properly. So people that the first shock when they buy this unit, they say, yeah, my firewood is perfect. I've been doing it all my life properly. And then they try to light a fire and they just run into issues. They can't even start the fire. And some of the units also have, like I mentioned, that lambda sensor to monitor the air-to-fuel ratio as the wood is burning and going through the last phase of combustion. That's our two pictures. So on the left-hand side, this unit is made in Austria, and the other one was fabricated in Manitoba. And they're essentially very, very similar design and size aspect. They were available on the market. Now the unit made in Manitoba, I think right now it has been, that company's been purchased by a company in the States, and that now the modification or improved version is now available for sale and has passed the EPA 2020 limits. And the unit from Europe is a no-brainer. It was passing the units, the emission test a long time ago. So the way typically that they would hook up, that's a typical piping diagram that's for one of my demonstration project at a small greenhouse where those two units were tested. So as you see, the heat load is not hooked up directly to the heating devices. They're hooked up firsthand to the buffer tank. And that's really a big difference with the typical legacy units for outdoor cordwood boilers. So what they typically said, I mentioned that you load the cordwood in the European unit, you do the startup, you have those emissions at the start. But when you go in the full output stage, you see that now it's measured here in parts per million for carbon monoxide. you see that they significantly drop, and then for almost 2 hours, and then you go into the charcoal burnout phase, which I said is quite difficult to handle. So you have a little bit more emissions during that stage, and then eventually, because the unit is equipped with a lambda sensor, it does measure the oxygen. It just knows that the flue gas is a lot colder and there's a lot of residual oxygen, meaning there's really not much burning at that point, and it's just going to shut down the unit. So now we're going to look into the automatically fed units. So pellet stoves, you also have pellet fireplace inserts and wood pellet forced air furnaces. Again, a lot of the advancements here is the automation. So some would have automatic startup. It's not always an option, but I think if we try to improve the test and certification method, people will probably realize that we do have a lot of emissions during the startup phase. Or just that idling is quite bad for the units. So when the burn rate is reduced to a minimum, that's also when you have a lot of the air emissions. So the newer ones are tested so that the minimum burn rates do not create a lot of emissions. But you still had a while ago the what were called the exempt pellet stoves. Essentially, they were circumventing an old rule that was drafted in the 90s that is now part of history, thankfully. But some of these models were still available a while back, so you do have to double check if your unit was not using that exemption status to pass the test, or just to not be tested at all. And I would highly recommend that you get rid of that stove and buy something that's up to date. But for the biofuel, you do not have the issues that you'd have for cordwood. I think the only thing to consider is that you would have to check for the ash content. So a lot of the user feedback is that, oh, these pellets from this company are a lot better than this company, but you don't actually consider why. So I think some people say, oh, they're softwood, those are hardwood, and they try to compare. I think really the issue here is that it's the ash content. So some of the pellets have more bark. It would increase the ash, and it does cause a little bit more issues with the in your appliance, especially when it's idling. So for the indoor units, for the hydronic heaters or the boilers, the European style one, they do come with automatic shutdown and startup. So obviously you have a lot less emission. They also have quite larger heat exchangers because they want to capture all the heat inside the water. So they have better residence time. And I think the thing here to understand is that the European test method would test down to 30% heat output, and after that it would, the unit would shut off. And for the US standard, they try to test down to 20%, but unit doesn't have to force a shutdown. So if it's a tricky spot to be, and that's why it's quite difficult to be in that spot. And that's if you go check for on the database for the compliant units for 2020, you do see that there, I think maybe one, or there was one unit that was looking to be passed, and all the other units, they're that European style, because it's quite difficult to achieve the emission tests all the way down at 20%. So the way that they've did it in Europe is they just force the unit to shut off until there's enough demand to restart. And some don't have lambda sensors. It's not necessary, but they'll invest more effort into the combustion air control. So they would have a variable frequency drive so that they can be able to ramp up and down and follow the heat output. So that's typically what they look like. Wood chip boilers would also have very similar, management of the Magic 7. The only issue here is for the biofuel itself. Right now, the supply chain is just developing itself, and wood chip quality and consistency is the issue right now. So I wouldn't recommend them for residential or farmstead application unless you would handle, uh, chipping, storing, drying, removing the fines yourself, as we've seen in the second session. But they're a great type of appliance for large multi-residential, commercial, and industrial applications. When you go into economies of scale, the price of wood chip is a lot lower than wood pellets. So that's when you would be able to recuperate the higher capital costs for these indoor wood chip boilers. So now we can jump in the emission control. And when I tried to explain how automation made a difference in the appliance that we just seen, I always talk about the advancement of electronic fuel injection for gasoline and diesel engines. They also use a bunch of sensors, and actually a lot of the technology for the automotive sector has made its way in the early 2000s in Europe in these hydronic heaters. So they were like early type of lambda sensors that you see on the picture that were installed. There's also all sides of sensors that were installed to monitor the temperature, check how much air is coming in, and we even have exhaust gas recirculation for wood chip or larger wood pellet boilers to help control those Magic 7 that we just mentioned. So like I said, in about early 2000s, end of 2000s, you'd see that typically the emissions was a lot reduced because of that automation and those sensors. There's also the thermal efficiency. We could have another quick 1 hour talk just on thermal efficiency of these appliances and compare them with the stoves, furnaces, and fireplace inserts. But yeah, let's keep going on the combustion. Like I just mentioned, what we do have a key sensor is that lambda sensor here. So it monitors the air to fuel and tries to maintain about 30% excess air, or lambda of 1.3. That means it's about 7% wet on a wet basis, residual oxygen in the flue gases. That's what's really trying to do, and the appliance will try to control the primary or secondary air to hold that sweet spot. So how did it look like? So this is an indoor European style cordwood boiler. It does have what's called a two-stage downdraft combustion. So on the top part, you'd have where you put your cordwood, where you'd light your fire, and then at the lower combustion chamber, that's where you'd have the secondary combustion. That's really where you would see the flame coming out. You wouldn't really have a fire in the primary combustion zone when the unit is in normal operation, but you'd have pyrolysis, so you just really the wood would be cooking in there and smoking, and then that's key, is to separate those two phases, so that you just focus on burning the volatile fraction of the wood, which is 70% of the wood. So that is a different type of appliance. That is an automatic wood pellet boiler. Actually, in this picture, it was burning switchgrass pellets that we supplied for testing at Cornell University. So it had two holes to secondary air input into that the back of the combustion chamber. And as the fuel is being fed, it's moving down the grates, and I think two of the grates are moving, and it keeps pushing slowly but surely the pellets as they burn. And then at the bottom, you don't see, but they would eventually fall into the automatic ash removal. And that's that picture, what's called, it's an updraft, two-stage combustion. So like I mentioned, the emission control. So once you master the Magic 7, that's when you really try to apply secondary measures like multi-cyclone baghouses, which are just large filters, or even electrostatic precipitators to remove them. So in that large power plant that we see, it's called the Copenhagen, and it's the unit that was a lot discussed during the Copenhagen Climate Conference, um, because people were planning to do to ski down this power plant with some like synthetic grass, and then it does attracted a lot of attention during the conference. So they use catalytic converters. So you can have stoves that do have catalytic converters, but again, the way I talk about it, it's a secondary measure. So it's really sort of a band-aid solution to the issue of not being able to control the 7 factors for proper combustion. And because once they're installed and out there in the unit, they do have to be maintained and their performance verified by the operator. And this is something a little bit more difficult to do. And then you would have either on the larger units, you'd have selective or non-selective catalytic reduction to remove NOx, so to minimize their emissions. Again, thermal NOx, a bit like diesel or gasoline engine, is created because of the high temperatures. So one factor is to try to control the temperature, but you still have a little bit of NOx coming out of there. So they would use SCRs to remove that in their larger units. So that's an example of multi-cyclone located in a greenhouse in Ontario, tomato greenhouse in Leamington or Kingsville. I think it's in Leamington. And then there's all these other options that help for combustion and controlling the emissions. But you'd have a whole slew of options that are focused on the safety aspect to maintain, to make sure that you don't have an issue with the appliance. There's also other options like automatic ash cleaning in the fire tubes, so where the smoke goes and where the ash would accumulate. Some of them would have some kind of automatic, either if it's a brush that you can do it manually, or it's done automatically, so they would inject pressurized air to clean those tubes, and after a certain point you have to go there and remove it manually with a brush. So not a lot of the sensors that we mentioned already there. I think another one would be the low pressure monitor. So we'd try to make sure that the draft is in, again, the proper sweet spot to help the Lambda sensor make a proper informed decision on what's really happening. The more you know, the better it is. So that's why automation exists. So there's a couple of other considerations for the heating systems. The first one we've discussed is I've talked about buffer tanks, and something it's quite new here in North America, their use. Essentially, it's just the way that they're hooked up to the an existing heating system. It has to be carefully considered because it does have an impact on the combustion and the thermal efficiency, because it does reduce idling. So depending on the size of that buffer tank, sometimes you just design a buffer tank to make sure that the appliance, when it shuts down, it properly cools, so it gives the excess heat just in a tank. Or you want to design that the wood heating appliance would provide heat for the building for an hour, an extra hour, or an extra 2 hours before the unit would be able to restart. So depending on the application, that's essentially how they work. You'd have essentially the buffer tank in middle, and the wood boiler would be recharging this thermal battery, if you want. So typical application of this concept for a small flower greenhouse is a 50 cubic meter buffer tank that is being heated. So during the day, essentially the farmer is recharging that buffer tank, and at night, so he does go in there, load the boiler as best as he can. Well, so this wood will be burning throughout the night, and eventually when the whole batch has been burned, then the buffer tank would provide an extra couple of hours until the farmer would have to wake up in the morning and reload the unit, because the heat load on double poly greenhouse is massive. The amount of heat that they require is a lot. So if you don't want to get up at every 3 or 4 hours throughout the night to recharge a boiler, that's why the buffer tank helps a lot. So there's some air approvals if you're that are required. If you're residential, you'd be requiring a building permit, so you have to check with your municipality. They enforce that part of the Ontario Building Code. Other provinces would be probably a similar application. Every province is different in that aspect for the residential section, residential sector. And in Ontario, if you're multi-urban, commercial, institutional, or industrial, you would require provincial air approval. There's two pathways. There's either the environmental compliance approval or the quicker and faster process, easier process, and that requires that you use an European unit that has been tested and certified. And that would help your the process of your application permit. So you have to contact the approvals branch if you are planning to do a project, and they would provide you with the guidance document. So the link to the guidance document is the first reference that we have on top there for small wood fired combustors. And if you do want to access the webinar, you can Google it. You can also have access to the technical report from IEA, the International Energy Agency, for Task 32. You also can Google my fact sheet that has a lot of the pictures and points that we mentioned. And if you do plan to integrate a hydronic heating system or wood chip boiler, wood pellet boiler, I'd highly consider you look at the a UK handbook, although it's getting a bit dated. This, it's 6 years ago. It's quite current, and here in North America, this is completely new for us. Very few people know how to properly do it. And this design guide is really essential to make sure that you properly integrate your system in your building. And I think that's it for me. I'm looking forward for the questions.
Great, thank you very much, Terrence. I really appreciate how you broke down each system by those magic 7. Mm-hmm. That was a great way to do a comparison between the different options that are available. Mm-hmm. So based on the time, we're going to move on to the question and answer period. And Devinder, if you could bring up the summary, that would be awesome. We have a wide range of participants that are partaking today, so that's great to see. Thank you for finishing up or completing the poll earlier today. So we have a couple questions to begin with. So early on in the presentation, there was a question that came through here asking if you can elaborate on the toplet startup for wood stoves. How is it done and why is it better?
Yes, there you can access the, there was a special report also available on the IEA Bioenergy Task 32 website that was done by Thomas, and essentially is instead of having the paper and the kindling at the bottom of your stove and then put the larger pieces on top and then light or start that fire, you do the opposite. You simply put the big pieces at the bottom, set the kindling on top, and then have the newspaper light up. So the idea behind that is that you get to that hot temperature, proper turbulence time, and proper air to fuel ratio right away, instead of waiting for that initial phase of all the batch of wood to be in the proper sweet zone. that's essentially how it's done. It does take a little bit of trial and error to properly do it, but it works.
Okay, thanks, Terrence. And just a reminder to our participants, if you have questions, on the side here is the website and the participant code for entering in your questions. The next one I can answer that the presentation will be made available afterwards. And we have a question from Gord with WPAC. You have shown that the European pellet boilers are highly efficient and low emission. Why are regulators opposed to their use in Canada?
Interesting question, Gord. So Gord's from the Wood Pellet Association of Canada, and as we've discussed with Gord that beforehand, many times over the years. So Canada produced, almost 3.2 million tons of wood pellets. Most of them are exported in Europe and Asia to produce power or heat homes. And why are regulators opposed? So there's a couple of issues. The one is just that they don't pass the emissions tests here. And like I mentioned, I did talk about the US EPA, and then there's the European test. So the test that's done in Europe is not recognized in Canada. There are some efforts that are done to be there. I'd interest anybody that is involved in this or would like to have more of these appliances to, start a conversation, talk with people, see if you can get involved in this. And the other aspect is that just for safety. So the standard that's used in Europe is not recognized here for safety. So their recognition of the pressure vessel regulation in Canada. And no, so in Canada we use the ASME one from USA, but we don't recognize the one from Europe yet. There's some jurisdiction like PEI has done a lot of work to access those because we don't really have a large manufacturing base to produce these units here yet. And until then, it would probably make a lot of sense to consider using the equipment that already works in Europe and try to make this work. Okay, have more questions. Let's go.
Great, thanks for that insight, Terrence. So our next question, for chip-fired boilers with capacities between 300 kilowatts and 1 megawatt performance, do these units are manufactured in Quebec perform as well as units manufactured in Europe? Are you able to address that one?
Well, I'd have to check at the test report how they're certified and what they do, because there were units. Essentially, the intellectual property was coming from Europe, and then they were assembled in Quebec. Or there's also some companies in New York that have done the same thing. They've used the IP from Europe and are being essentially built or manufactured so that they would fit the ASME requirements for boiler pressure vessels. I've heard some have done well and some have done very poorly. So your mileage may vary. I guess it's the experience also behind the many years. Some companies, they produce like 15, 20,000 units a year, and some would just make 1 or 2 a year. Buyer beware, I guess, is at this point. What can I say?
All right, and based on time, we're just going to tackle these next 2 questions before we wrap up the session. So is the Polar Manufacturing cordwood boiler an outdoor unit or just indoor?
Yeah, I recall for that certification, it was a dual. So it was either outdoor or indoor. It was CSA certified to be used indoor. But again, reloading it indoor was a bit of an issue for these units. And also it's not really set up to be hooked up to a buffer tank. So you would have to go in there and modify the unit. And whatever you do modify a unit that's CSA certified, you essentially void the certification. So I wouldn't really recommend using this unit if you want to modify it. Let's put it this way.
Okay, great. Oh, sorry, Terrence, go ahead.
No, I just see the other question because we're almost going to run out of time. Is I just Google it. Just Google small biomass boiler technology. I'm probably the third or fourth down there.
Excellent. Okay. So that is all the time that we have today. Thank you, Terrence, and thank you to our participants. I hope you have enjoyed today's session. Before we sign off, I'd like to send out a friendly reminder to register for upcoming sessions, which you can learn more about by visiting cribe.ca/resources/bioheat-webinar-series. Sessions will continue to be held weekly on Thursdays until March 11th. Next week, we'll be back to learn about project planning with Cara Sanders and Jordan Hatton. You can find registration links for this February 24th session by visiting the CRIBE website. We are looking forward to having you join us again. If you have any questions or comments about the series that you would like to pass along, please contact my colleague here, Jonathan Hellis, via email, and he'll be happy to help. That concludes our session. Thank you and have a fantastic day.
Thanks, Karen.